Hey guys, this is Mr. Poe. I just thought I'd make a video for you guys to talk about the chapter that you're doing right now, chapter 11. It's called chi-squared tests. It's not called chi. Do not listen to Mr. Bowles. He likes calling it chi, but it's pronounced chi, C-H-I. There are three types of chi-squared tests. Section 1 covers goodness of fit, and that is abbreviated GOF. Section 2 covers homogeneity and association/independence. I'm going to cover those two in another video, but today we're going to look at goodness of fit. Chi-squared tests are used with categorical data, and in the real world, they're what a lot of times we hear about on the news or on the radio. Like anytime somebody asks a question like, do intelligent people cuss more than dumb people? Are Southerners more religious than Northerners? Those type situations involve two different categorical variables, and we have not covered that. We have not studied anything yet that deals with two categorical variables being studied at the same time. And so that's what happens with chi-squared. But today, like I said, we're going to look at the goodness of fit. Now, the goodness of fit cannot be done in the TI-83. I told you guys at the very beginning of the year that you were going to want to rent a TI-84 because the TI-83s do not do everything. And this is, we've seen it already that there's some things the 83s can't do, but this is the big thing that it cannot do. If you are doing a goodness of fit test and you're using a TI-83, you're going to have to do it by hand. You're going to have to find the chi-squared value by hand because the calculator cannot do it. But if you've got an 84, you're in luck. So I thought that what I would do in this video is go through one of the problems in the book, page 692, number 7. Hopefully you guys have already done this, but if you haven't, I'm going to walk you through it so you'll know what needs to be done in a chi-squared goodness of fit test. All right, so this is dealing with the trees in this Oregon forest. And with a goodness of fit test, what you're doing is basically you've been presented with a list of proportions that are claiming to be true. And then you take a sample, find your own proportions from that sample, and you're trying to see, does your sample match the claimed proportions? The example that the book did in the section, if you guys read it, was the M&Ms, the color of M&Ms that Mars Incorporated, they report that a certain percentage is green, a certain percentage is orange, and so on. And then in the problem, you take a sample, you find your proportion of each color, and basically you're seeing, do you think their claim is true or is it false? And that's what you're doing with the goodness of fit. It literally means how good does your data fit with the projected claims of proportions. All right, so let's go through this problem, number 7. Obviously, you're going to start out by naming it chi-squared goodness of fit test. Now, don't put GOF test. Don't abbreviate that. Put goodness of fit. All right, next we have the null and alternative hypotheses. There's not really a proportion to define, or not proportion, but a term to define like we have in the past. So the null hypothesis, what you're going to want to do is write it with a whole bunch of equations. For instance, proportion, let's say 54% were Douglas firs. So I'm going to say proportion firs equals 0.54. Then it says 40% were ponderosa pines. So proportion pines equals 0.40. And 6% were other types of trees. So proportion other equals 0.06. So that's your null. You just write out a whole lot of different proportions. You do not have to write firs, pines, and other. You can call them P1, P2, and P3. It doesn't matter. But if you do that, then you're going to have to say where PI equals proportion of a specific type tree or something like that. But if you do this, you don't have to put the where PI equals something. So a lot of times I'll just do it like this instead of P1, P2, and P3. The alternative is going to be at least one of these P's is incorrect. All right, so that's P subscript I. So at least one of these PI's is incorrect. All right, now the conditions. If you've read the book, if you've read this section, you know that the conditions are a little different now. And when I say little, I mean little, just slightly different. Conditions, random is still there. It needs to be random. And randomly selected is stated. Now, the chi-squared curve, if you notice on your pink sheets, it's not normal. It's right skewed, and it's supposed to be right skewed. So obviously, we're not checking the normal condition. That doesn't make sense because it is not normal. It will never be normal. In place of normal, you're checking large sample size. All right. And for large sample, what has to be true is that all expected counts have to be at least 5. All expected counts have to be at least 5. And we're going to list those out in just a little bit, but I'm going to go ahead and write all expected counts are greater than or equal to 5. And then independent let's see. The sample size was 156, so we must assume there are more than 1,560 trees in the forest. All right. So now what I'm going to do is I'm going to get out the calculator, the TI-84. And when you go to stat and go over to tests, go all the way down, you'll see chi-squared test and chi-squared goodness of fit test. So we're doing goodness of fit. When you press enter, you have two things you're looking for, observed and expected. And notice list 1, list 2. So we have to put our observed and expected counts into list 1 and list 2. So I'm going to back out of this, go to stat, go to enter. Got to clear out my lists. All right. So list 1 is observed. So the actual observed amount of each. 70 were Douglas firs. 79 were ponderosa pines, and 7 were other. Now, list 2 was the expected counts. To find the expected count, you take each of the proportions that go with the corresponding, in this case, the corresponding types of trees, and multiply it by the sample size. So 54% were supposed to be Douglas firs, so we do 0.54 times the sample size of 156. press enter. Now, a lot of times you're going to get decimals. Leave them. Don't round them. Expected counts, we know from chapter 5 or 6 or whatever, that it's okay for expected values to have decimals. All right, next, 40% were supposed to be ponderosa pines, so 0.40 times 156. And then 6% were other types, so 0.06 times 156. Press enter. Now, what I'm going to do right here is I'm going to put this data onto the paper. Just under observed, expected. 70, 79, and 7. And then expected 84.24, 62.4, 9.36. You need to put this data on there, and also just not only to have the data on your paper, but also to confirm that all expected counts are at least 5. So these numbers are all at least 5. Observed counts don't have to be greater than 5. I mean, they were in this case, but all you have to check for when it comes to large sample is the expected counts. Are they greater than 5? All right, so now that we've got list 1 and list 2 taken care of, I'm going to go back to the tests. I'm going to go to goodness of fit. Observed was list 1, expected list 2. Now, degrees of freedom is the number of categories minus 1. We had 3 categories: firs, pines, and other. So that 3 minus 1 is 2. Calculate. And there's our chi-squared. So for this, we put the generic form of the chi-squared equation. This is at the bottom of one of your pink sheets. It's the sum of observed minus expected. Hold on, let me get it right. I want to make sure I get it right. Observed minus expected squared over expected. All right, so you put that. Now, so what I was saying earlier about the TI-83s not having the goodness of fit, if you're using a TI-83, you literally have to do 70 minus 84.24 squared over 84.24 plus 79 minus 62.4 squared over 62.4 plus 7 minus 9.36 squared over 9.36. You have to do that by hand because you do not have a choice. But the 84 produced the chi-squared value. We got 7.418 and a p-value of 0.0245. And now the conclusion. Since our p-value is less than, oh, I forgot to put an alpha. I don't think that they told us what alpha level to use, so 0.5. So let's write that somewhere in our data. Alpha equals 0.05. Notice that there's no like sample size or mean or proportion that we had to put. Really all we needed to put was the observed and expected counts and the formula. All right, so since our p-value is less than alpha, we reject the null. We have convincing evidence that now you have to go back and look at the problem. It says, do these data suggest that nuthatches prefer particular types of trees when they're searching for seeds and insects? All right, so since our proportions did not match the proportions that were given, then we've got evidence that they do prefer certain trees. So that's how we're going to word this. We have convincing evidence that nuthatches prefer particular types of trees or particular tree types when they're searching for food. Because if they did not prefer certain types of trees, then the observed values should have matched the expected values a lot more. And you can see they were different. We observed 70, but based on the proportions of trees in the forest, we were expecting 84. Here we observed 79, but we were only expecting 62. These two were pretty similar, but we can tell that these were quite different. All right, so that's how you do a goodness of fit test. If you guys have any questions about anything, please send me a remind and I will get back to you as soon as possible. I will be sending you another video that deals with homogeneity and association/independence.